Hello, welcome back to Hyperthesis episode 36 now. Wow, 12 times 3, 3 dozens. That's great. My name is Pheely.
I'm Patrick.
I'm Liam.
And I'm Dean.
As you can hear, we have a guest today, Dean Eaton. So he's going to be talking to us about his work and partly his life. So welcome, Dean.
Thank you.
All right, before we get started, let's
do
go
a
to the
little introduction of Dean quickly before we do our intro topic, maybe.
No, I'll gotta hop on intro topic.
All right.
So, our intro topic today, I'm gonna think about, well, I started thinking about the robotic physics. I don't know if people have heard of that. But I was at a March meeting conference and there was like a few sessions, actually quite a few sessions on robotic physics, and I didn't understand. Like, well, I mean, like, why do we care? And the reason for that was that my colleague was like, well, you always go to at least one robotic physics session because they always have nice videos of figures of robots, which are fun. But in a way, it's quite interesting that I thought differently because I thought like robotic stuff is just engineering, but there's a lot of physics that go into it on how actually the robots move or traverse through space. Basically, what's the mechanism of that? That's like, oh, if it's flying, how's air work around the propeller or some kind of wings, right? So in a way, it's a mix of like aerodynamics and bunch of mechanical, maybe different like and some did have like different implications on like the current theory, maybe of like even quantum stuff. Pretty interesting.
Yeah, I didn't realize robotic physics was a thing until about last week when I saw a YouTube video. I think a couple million people have seen this video by Mark Rober on delivery drones. But an interesting aspect of that was that they had a newly designed propeller, which looks nothing like any propeller that I've seen before. It's this weird kind of like Y shape, almost looks like, I don't know, an X chromosome, where there's like a shorter end and a longer end. But there's a lot of simulation that goes into that and a lot of physics. And then it's also kind of biomimicry, which we've discussed before in there. But it's just for a simple propeller, there's a lot of physics that goes into optimizing them. And the really cool thing about this propeller was it was a lot quieter. So if you've heard a drone flying overhead, it has like that whirring, like that noise, whereas this was more of a white noise. It didn't have peaks and very high frequencies. Instead, it was pretty solid throughout. So it had this essentially white noise that kind of blended in with the background. And so there was a lot of physics research and then also engineering that went into that drone propeller. So what else did you see in terms of robotics at March meeting? Like, were there any specific research examples that stuck out to you?
Honestly, it's pretty not my thing. I was like, well, it could be interesting to some people, and I was like, I would never ever do that stuff. And it's like, okay, but they have like flying drones and I mean like videos. But well, why I brought it up because it's such a, in a way, different type of way to think about physics, I think, rather than what we're doing, but especially Liam and I, where we just like stare at paper or screen, and now we actually have see some actualization of things that some of the theory that we see in a way pretty advanced way. It's not just like, oh, I'm gonna have Cartesian coordinates and just like, oh, things going, let's say like really simple description of robots, right? Or like how they move through space. They're actually quite complicated.
Yeah, I was thinking about this earlier about how, I don't know, the stuff I study is very much like, it's kind of far out, man. You know what I mean? Like, it's, I don't know, black holes, they're cool, but realistically, they're not gonna directly change the Earth. But I thought it was cool. I was watching this talk online about Kelvin ship wakes. At that at some point I was in England for a conference for a month, and I talked about that before. And there's a talk from that which I missed. I think I slept through it by accident, unfortunately. So I was going back and rewatching it because they recorded it. One of the good things about COVID is that a lot of things are recorded now. And all the exact same kind of techniques I learned in math and asymptotics and all this stuff, it just showed up in this field, like describing actual, water waves produced by a ship and describing like why they look the way they do and how you can modify them and change their shape. I mean, they all have the same kind of shape, but like how you can change their amplitude and things depending on certain parameters. So it gives me hope. It gives me hope that, if black holes don't work out for me, I can at least like go study something in the real world, and use what I've learned there. And I think that's kind of what you're saying, Pheely, about how like, yeah, we don't really study these kind of like real world things, or like not in like a direct sense. I guess we're doing kind of more abstract things, but I think that still can pay off in some way.
I can't say I relate anymore because I literally deal with things in the world like forests. But uh, going off of what you said, Liam, there's actually a couple people that do s- physics simulations, but of the world. And so one of the professors at the University of Alberta looks at different types of waves that are naturally occurring, whether they're gravity waves in the ocean or in the air, and other types of waves, and then applies that theory and those model to ways in which, for example, we get nutrients from the bottom of the ocean, or how we get turbulence over mountain ranges, and trying to not necessarily predict that turbulence, but see its effect without actually having to go into the real world. So that's good that you got the opportunity, Pheely, to see some, I guess, applications and get inspired by it.
Speaking of like the robotics earlier, have you guys been checking out the Boston Dynamics stuff going on?
Not for a long time.
They have arms now. That's terrifying.
Have you seen the video of the new guy that they have that can like turn and pick up a bag and bring it up like scaffolding to like somebody doing construction work?
Ooh,
And doing like a cool backflip?
So just to describe the video, so the Atlas robot that they've been working on for many years, it's a bipedal robot, so it has 2 legs, 2 arms, and they've done some super cool videos. Go search up Boston Dynamics on YouTube. They have it doing parkour, it does backflips, it does dance, and in their most recent video, they give it actual like working arms instead of just little knobs to help counterbalance it. So it's actually able to pick things up and move them. So in the video, it's able to pick up a board, then picks up a tool bag, runs across the board that's placed, throws the tool bag up to a worker, and then dismounts with a backflip. So it's incredible that now they've added working arms to this already impressive robot.
I think one of the most impressive parts about adding that is the fact that it's adapting to its own environment. So it wasn't told to pick up the board and put it down, which it needed to like further progress itself through this path to get to where it had to go. It thought on its own, I need this board to move it here in order to get from A to B to bring this up on the scaffolding. Like nobody sat there with a controller going, okay, let's pick up the board. Like it did it all by itself through AI.
That like machine learning, it didn't. It's done enough things where it's kind of figured out how to get around obstacles, or how does that work?
If I remember correctly, I think it was kind of programmed. So these robots are very adaptive in how they interact with the environment. But from what I understand, there's also a behind the scenes video and a couple blog posts and other related media. It was still programmed to like pick up everything. And so there's a whole bunch of behind the scenes videos where it's failed to do this many times. But it's able to do a lot of interpolation of, okay, you want me to pick up the board? Where's the best place to position it? How do I walk across the board the best? So there's still a lot of like feedback algorithms for it, but I think there is still some human interaction in telling it what to do, because they did this many times before they got the shot that we see in that video.
I think we're going about this wrong. I think we're close to an AI revolution, the AI uprising. We've got like Chat GPT, we've got these AI art things, the AI voice mimicking. We've now got robots that can do things. the wrong person puts those all together into one robot, I think that's it for us. I don't know. Like, pretty good. It's really cool, but it's really scary at the same time. I mean, we're still a long, long ways away from that, but who knows, man?
Well, I feel like you've been watching too much iRobot. Well, I don't know if kids these days are old enough
No,
to watch that movie.
I've
even
never
that
even
came
seen
out.
that movie.
Shame, but you've seen Terminator, right?
Yeah.
Okay. Anyways, I think we should move on to the main topic of our guest. So Dean, Mr. Dean Eaton here is a master's student at University of Waterloo, working with actually the group of for Donna Strickland, which is a Nobel laureate. So I think he's working on some laser technology. So I'll let him tell you a little bit about it and in his own words.
Yeah, so I work in the ultra-fast optics group. There's so many different names you could call it, because we do ultra-fast stuff, we do photonics, we do nonlinear optics, and nobody's on a sort of consensus of which one of these do we pick to call ourselves. But working in Donna Strickland's group, I do mostly the experimental side, a little bit of simulations. My master's has more or less just been focusing on getting our laser system up and running to this point. I arrived here in September 2020, so fairly towards the start of the pandemic, and the group is fairly small, and I get there and it's like, we got a laser, but nobody's here to really maintain it, so 9 months later it's broken because nobody's allowed in lab. And then most of my time has just been, how can I fix this? How can I fix that? Typical stuff that happens in a physics lab is, expect something to break every week and you won't be surprised. So that's up and running now that my master's is pretty much done. I'm in the last couple weeks of more or less getting my thesis done, setting a date to defend, and starting my PhD here in the same group, just continuing.
In these laser labs, I mean, I've seen your lab. You took me for a tour once, but like just in labs in general that have optical setups, you have, I forget what those boards are called, but they're these big metal boards with holes in them everywhere, and you can screw things in and set things up.
Breadboards.
And breadboards, yeah, it's like a bigger version of an electrical breadboard. It's just for not electronics as much, and more for like actually putting things on it, and lenses and mirrors and.
Yeah, it's just a big metal table with evenly spaced out screw holes.
Yeah, so those breadboards, I know that in a lot of these optical labs, the setups you have like bouncing lasers around and splitting beams and recombining them, they're so complicated that if you like breathe in the wrong direction, they unalign, or you shut the door too hard.
So that's one of the reasons with our laser is we use it's a all normal dispersion fiber laser. And even though it's it's supposed to be a fiber laser, there are still free space components, so like your more traditional parts. And those are usually the parts that require little bits of tuning, provided you don't break any of your fiber optics, which can happen by accident just through wear and tear of running it for so long.
Oh, so we're going to be talking a lot about lasers, and especially these very quick, high energy lasers. So can you take us through how they work and just kind of outline the kind of setup they require to operate?
Do you want to talk about more general lasers or more of the specific type of laser I'm using?
Why not both?
A quick general laser.
A quick introduction to laser followed specifically with these ultra-fast lasers.
Okay, so a general laser requires just 3 or 4 different things. You need some way of getting a light source. Usually you can just buy sort of light pumps that just pump large amounts of continuous wave light down a fiber or just straight into free space. You need some way to get gain, so some material that has these energy levels that you're stimulating to get coherent light out of it. And you make it coherent by then oscillating it back and forth and back and forth and back and forth. And so those are more or less, and you need some way of getting the light out of the system. So a lot of them might use a semi-transparent mirror, so that way some of the light's bouncing out of the cavity. What we use for our stuff, though, since we're mostly fibers, is we have this small piece in free space, and basically we just add a polarizer. And so light has different types of polarizations. What we do is we just add these polarizers to adjust it, so that way it's all linear. So polarization is either only in the X plane or only in the Y plane. And what we do is we just add a polarizer into it. And what the polarizer does is it says we don't know which one's X and which one's Y, but let's just say if you're X, you're going straight through, and if you're Y, you're coming out to the side, sort of reflected as if it was a 90-degree mirror. And so by putting a fiber pump connected to these fibers, and then using fibers that are doped with rare earth elements, for us, we use a ytterbium fiber. So that's our gain. So now we're making the right color light with an energy source, and then we just connect the input and the output of the fibers pretty much together with that little bit of free space in between them, and now we have a way of just circling it around for oscillation. And because of that polarizer, we get an output that's already linearly polarized coming out of it, nice and simple.
Quick question, what color of light? Or what wavelength?
So it's typically centered somewhere around maybe about 1030 nanometers, maybe just a few nanometers above that. But because of the way this laser works, and we're using a lot of nonlinear effects in our laser, because we're using such a small core diameter that the intensity in the light causes these nonlinear effects in the fiber optics, we get what's called SPM. And this is one of the things that, like, the last several months I've been writing my thesis is a lot of reviewing the one particular nonlinear effect, self-phase modulation, that, although we just shortened it to SPM. And what happens is as this goes around, you actually get a bit of a spectral broadening, so you get more color out, rather than a typical laser, which is very specifically tuned to a specific wavelength or frequency. And so we can get spectrums usually about 8 or 9 nanometers wide, which is a little wide for a laser typically. But because of this nonlinear effect, they actually have these really big edges on their spectrum on the outside, and the middle is a lot less powerful. So what we'll actually do is, once it's outputted, we put in a bandpass filter, which only lets some of those colors through. And so we'll adjust it so that way we're taking one of the two peaks on the edges of the spectrum. But it's typically about a 1030 nanometer spot.
Oh, since you're working on ultra-fast laser, well, what makes it ultra-fast? And in your opinion, like, why would people want ultra-fast laser? What do you use it for?
Yeah, don't they all move at the speed of light? You can't have ultra fast when they're all the same speed.
So the point of the laser is that it's pulsed. It's not just continuously running like the pump would for the laser. So you're getting these sort of quick peaks and then a long rest period and a quick peak. And so you'll keep track of the repetition rate, which is how often they have these pulses. And then the ultra fast part is how fast that pulse actually occurs. So you'd look at typically a full width half maximum. So you're just taking half the intensity of the maximum on the pulse and then just figuring out how wide that is at half of that maximum. And that's how long that pulse duration is. Sometimes it doesn't always play nicely because you may or may not have a nicely shaped pulse. Like, it may be a nice Gaussian, or it may be some junk, and you got to figure out what that junk kind of is just by roughly guessing. And sometimes you get these large peaks, and it makes it harder to determine, should we use a full width half maximum, or should we just go, it looks generally this broad type of thing. But anytime these pulses have a pulse duration of usually about a picosecond or less, you start to consider them ultra fast. And so for our laser, just the laser part without a compression system to make the pulse shorter is already outputting something on the order of, like, we're hoping for our new one that we're currently building to get about a picosecond. The current one's doing about 6. But you would add compression systems to this afterwards, and there's a limit to how much you can compress based on how much color you have. But ideally, we can compress the current one down to something like 200-300 femtoseconds.
Ooh.
Yeah.
Wow. Femtosecond range. Yeah, that's like the current. I don't know what the current limit is, but I know the really, really high power lasers are always femtosecond ones.
That has to do with more towards my PhD. Is we're doing sources where my whole PhD project is basically, can I make a single femtosecond or less source from the starting laser system? But to get back to your other point quickly, Pheely, about the applications, there's so many different things, because a pulse only has so much energy in it. And so that energy is spread out over the time. So if you take a pulse and you make it shorter and shorter, that peak intensity on that pulse gets higher and higher. And so a lot of things you need specific energy, like pulse powers to hit peak power. But there's also things like ultra fast imaging. So when you want to image like chemical and molecular interactions, you need something that has a resolution that can keep up with that. And that's often what a lot of ultra fast people look at.
Yeah, so to me is when you have really short powers kind of strange, because imagine your wavelength is, let's say, 400 nanometers, right? It's like 400 nanometers. And let's say 1 picosecond, it's a tiny part of that 400. So it's not even like maybe less than 1% of the, if you look at the waveform, right? Like how do you know is that it's exactly that frequency? Because like, well, you can't measure all that wavelength because you don't even have the full wavelength worth.
So you're talking about sort of a chirped pulse, I think. So a chirp and a pulse is sort of, as the pulse comes through, you have different wavelengths at different times throughout that pulse. And that's sort of what compression is about, is that the limit of compression is sort of when all of your colors are arriving at the exact same time. And as it spreads out, your pulse gets longer and longer. And so when you have a lot of the ultra fast pulses, it's when you're at your limit of when all the colors are arriving at the same time. If that helps answer your question. I don't know if you have some follow-up that I could explain more there.
Well, I don't think that's what I was asking, because if you think of wave, like light as sinusoidal wave, electric field, you look at electric field, for example, the wavelength would be, let's say, 400 nanometers, but your pulse is only picometers, right? It's a short part of it. How do you know is that wavelength? Because to get that wavelength, you have to travel at least 400 nanometers to actually see the waveform.
So I did just do the quick calculation, and the time it takes, the distance light travels in a picosecond is about 300 micrometers. So you get several wavelengths in that space.
Also, you have to be careful when you say light's a sinusoid, or it's like, because it depends if you're talking about like a continuous stream or plane waves or a wave packet, because like a wave packet's a bunch of plane waves merged together of different frequency into one. So you have to be careful what you say when you mean wavelength, I think. But yeah, like Patrick just said, that light pulse would go over a micrometer range, so it would. Well, I guess
the group velocity is different from phase velocity.
Yeah, so you got to be careful.
But if you look at electric field, though, it's gotta be somewhat sinusoidal, right?
Yeah, but like the wavelengths themselves are like, we're talking about a micrometer in wavelength, right?
Mm-hmm.
Like 1,030 for the color for the laser, and it's traveling over some distance of 10, 20 centimeters to meters, typically, between things.
Okay, so it has enough time for you to actually measure the wavelength.
Oh yeah, that's never really a concern. The concern is you can have concerns of measuring pulses when they get faster and faster, and that's sort of a whole branch of photonics, is how do we measure these pulses as they get faster? Because you can think of something like a photodiode, which just measures, is the light there or not? It has some response time of how fast it can pick up a signal, and then how long that signal sort of takes to decay on the detector. And so even though our pulses, we can have them compressed down to a couple hundred femtoseconds, when you put it on the photodiode, if you were trying to measure it on like an oscilloscope, it's going to look like it's like nanoseconds long. So there's all these new types of methods that come out. I remember doing an ultrafast spectroscopy course, and one of the things we talked about was using nonlinear effects by basically having this fast electric field vary through a crystal that then you can measure how the crystal's light changed very quickly. And that's one way of doing it, but that's a very active sort of field, is how do we get better as these times get shorter and shorter.
So in your kind of experimental setup, it didn't seem like it when you described it to me, but I'm also really dumb, so maybe I just missed it. Your supervisor, Nobel Prize winner. She won. I'm going to talk about this later some more, but she won her Nobel Prize for this thing called chirped pulse amplification, which is basically just a way to make really, really, really intense not wave packets, but pulses of light or
Pulses.
laser pulses. I tend to use wave packet as a theorist, but not quite wave packets. Anyway, do you use that setup at all? Because you mentioned chirps at one point there. Do you do any of this chirp pulse amplification in your stuff?
So my master's was sort of fixing the stabilization of the laser so that way it stays in the pulse state, which was a problem we had when it broke, and then getting our amplifier up and working so that way we can go on to make a 2-color system, which is then useful in all the other projects we're doing in lab, which is everyone's more specific project for their PhDs. But as far as the amplification goes, what we're trying to hopefully get a paper on is comparing 2-color CPA to a 2-color nonlinear amplifier. And so there are all these types of advantages and disadvantages for doing both. So for CPA, something that's sort of a more specific disadvantage is that when you go to compress them down to get these fastest pulses as possible, you can make them more intense doing CPA, but there's a limit when you do CPA to how much you can compress it, which is more based on the fundamental method of CPA versus how much color's in the light. And so typically they're only compressible down to like 200 femtoseconds, which if we're already doing that out of our laser, the goal is to broaden that and get it even further down, right? Get it shorter. And so doing the nonlinear amplification, by finding the right conditions that we make that work, we're hopeful to get it compressed down to like 40 femtoseconds before we even go on to the project that makes it less than 1.
Okay. Before in one of our other episodes, Pheely mentioned that the way he described it was that when you do undergraduate research, everything's linear, and then when you go to grad school, everything's non-linear. And I think that's very true, because every time we have a guest, anytime someone comes talks about the research, it's always like, yeah, so we have these non-linear things, and I think it's just neat that that's the way it works.
That's like the whole point in optics, right? Like
Yeah.
if you learn anything in undergrad about optics, whether it's an optics or a lasers course, almost everything's linear. And then the first optics course you typically would take if you're doing optics at a university is nonlinear optics, which is a lot of basically anything to do with high intensity is going to probably deal with nonlinear optics, which is pretty much what almost everyone is doing in the laser space now.
Yeah, basically, we figure out the linear part really well, and a lot of crystal, for example, have like nonlinear optical properties, right? Like that's why people do this stuff. Even like in like photonics, people create waveguides, and those stuff are not linear either.
Yeah, and non-linear things are easy, quote unquote, because it's math you can typically do, but non-linear, like the equations you get, you actually just can't solve most of them, and you have to be really clever about making approximations or doing numerics or blah blah blah.
Yeah, I was about to say, a lot of the stuff with nonlinear optics you see can't be done analytically, or there's ways to do it approximations, but a lot of it is you got to simulate it, and you got to guess at parameters, and then you look at the results and you go back and forth and back and forth. And that's how a lot of these amplifiers work. Like working on simulations for the 2-color nonlinear amplifier is, okay, do we need to make the fiber longer? Do we need a shorter pulse duration? Do we need a longer pulse duration? Do we need more power to seed it with? And a lot of it's just plug it in, figure it out, go back and fix it. Did it get better or worse? And just keep going until it works. A lot of hitting your head against a wall.
A lot of fish in a barrel kind of thing. I have another analogy. I better not say it on the podcast, but yeah. So there's two main questions I have that I want to get out by the end of the episode. So I'm going to start with the one that's more on topic right now, and that is so what is it like working for a Nobel Prize winner? Because that's not something a lot of people get to do. So tell us what that's like, and then I'll come back later with my second question because it's a bit more off topic, but
it has its advantages and disadvantages. Since I'm an experimentalist, I need to order a lot of parts and put stuff together, and stuff breaks. And the nice part is that we're a small group, but we have enough money that like something breaks, we never really have to worry about it. We have the money to replace it. even though, we're not trying to break stuff and we're not trying to always replace stuff. And we have a lot of really old equipment in lab because of that. Some of the downsides is the fact that, your supervisor's a Nobel laureate and her job's to fly around the world giving talks. And so she's not always around and available right at the moment you might need her. So it's a lot of, she's in China, gotta wait because she's on an opposite time schedule, and it might take her a day or two to answer an email because she's on the other side of the world busy doing stuff, versus a lot of supervisors that it's just like they're in their office 8 hours a day. Odds are they're probably free and I can go talk to them. It's kind of surprising, though, having such a small group. You think a Nobel laureate would attract all these students who all want to come work for her, and we're just sitting here like, man, it'd be really great if we had some students who could come do this work.
A lot of people are probably intimidated by it, honestly, because I remember when I was looking at grad school supervisors, all the really like top end people who were, huge in the field, I was like, I'm not going to bother with them. Like, there's no way they'll take me.
I've talked to so many undergrads who are like, oh my God, it would be so cool to work for her. And then go, but she has so many students applying to her. And I'm like, we had one person apply last year and they didn't even come.
That's really interesting, actually.
Like, we have funding to hire more students. We just don't have the students to be here and actually work. And I think the other problem, though, is that a lot of it is experimental. And I think if you look at physicists, a lot of them prefer the theory. They prefer sitting in an office on a computer.
I don't think so. I think you have a wrong idea. You at Waterloo. Waterloo is known for the experimental stuff.
No, we got lot of theorists here.
Waterloo's the theory.
Perimeter.
Yeah.
Perimeter and IQC are almost entirely theoretical.
Waterloo.
But that's not Waterloo.
No, it's pretty much Waterloo. Yeah.
Yeah, it's a part of
us. Affiliated.
No, our grad students are there. Majority of our students aren't in a physics building. It's in IQC or in Perimeter.
Perimeter is like 80% Waterloo, at least.
Yeah.
Yeah, but it's not owned by Waterloo.
Yeah.
It's a Waterloo building.
It's part of our department. It's part of Waterloo campus.
Is it?
Yeah.
I thought Perimeter is separate.
Well, it's separate from the campus, but it's still part of campus.
It's weird.
So you get a Waterloo degree if you get the degree from Perimeter?
Well, you can. I think it's Waterloo or Guelph because we have a joint program, so there are quite a few Guelph people there.
Or McMaster. There's a few McMaster people who are just permanently at Perimeter all the time.
There's a lot of profs that sort of live around here that work for. There's like one off. Like there might be a couple people from Toronto or from McMaster.
Because I thought Waterloo is known for like engineering stuff, so I thought they were more into experimental stuff.
Well, that's the engineers, which is different from physics.
Yeah, like the Queen, for example, I think more known for experimental stuff. There are very few theory people, or like theory people that are not astro or high energy.
We do have a large astro group here. But I was reading somewhere that I think that we're like the 5th biggest in terms of physics grad students in North America. And we're like the 4th biggest for undergrads. Yeah, it's just like in pure number size. It kind of shocked me.
It shocked me too, because compared to like the United States, I don't think that number could be true.
Well, I mean, like, I think of like second year, and like a year's class has like 200, 300 students. Like just for undergrads. So like you add that up over 4 or 5 years, and that's a lot of students. Because a lot of our programs are 5 years, because we add co-op to every single program you could ever imagine.
Well, that's a good thing, but yeah, it probably has a few downsides.
Well, it makes it's good and bad. You earn your money, you get some credits, but it makes you stay here an extra year. You also don't have like really summers off here. Most students are in term or in co-op all year round. So we're used to doing 2 terms on, and then you get your summers off, where typically you might do research.
But I think when you said that I mean, I don't know how true it is. I haven't gone and done a poll where you said like most physicists like
I think if you take a poll, I think you'll find that a lot of people would prefer or are doing theory over experiment.
That's a tough one though, because
would you rather be sitting on a laptop, or would you rather be in lab bent over a desk at like a weird angle, reaching around to screw something in, and then sit there adjusting it for 12 hours, doing the tiniest of little finger movements to get it right?
Well, I think for me, like, I did theory because experimental stuff is just hard, in my opinion. So I was like, well, I'll just stick with theory because I'm good at it. But Yeah, any experimentalist that I've ever kind of met, they're also good at theory, whereas all the theorists are just good at theory. So I think being experimentalist is it's typically harder, I think, because you have to be a lot more clever, I think. But I mean, I'm not here to make fun of theorists. I'm a theorist. Like I get it. We're smart in our own ways, but the experimentalists have to be very kind of you need to be clever. You got to think of ways to get around things, and not just like physics problems, but real world problems like budgeting and
But
equipment
a lot of
and
funding problems for certain groups,
yeah,
like having to build your own stuff a lot of the time.
and lab space and during COVID, getting into lab, like all that kind of stuff.
Um, I think a former professor of ours once said that for theory, it's about a third of positions in terms of professorship or for grad school, whereas experimental has about 2/3 of the positions. So if you do experimental, you're more likely to get a job because uh, there's a lot more stuff I guess you can do with experimental because some of these big projects need people.
I think one of the key points there, though, is that like if you're rating that based on profs, those profs that have an experimental group have students that are then doing theory as well, whereas a lot of the profs that are doing theory only have theory students.
Maybe they have some numerical people, but yeah, I no most theory people don't have experimental students.
Anyway, to steer this conversation back to your research, Dean, so we know that a picosecond is what, 10 to the negative 12 seconds, of femtoseconds, 10 to the negative 15. But I'm curious about the powers that you're dealing with or the energies that you're dealing with. So if you were to, say, convert that short pulse, very short pulse, like picoseconds, 200, 400 femtoseconds into watts, what kind of power are we looking at over that short period of time?
So typically you would measure the average power using just a power meter you'd put in the beam's path. And so for the laser, you're dealing with a direct output of maybe only 50 milliwatts. By the time it gets to the amplifier to seed it, so right before the amplifier, it's probably down to about 4 or 5 milliwatts. And then the amplifier's output is like, we've cranked that thing up to like 2.5 watts output. And then the goal for the 2-color amplification is to crank that up about another factor of 3 or 4. So we're dealing hopefully with about 10 watts on the end of the second amplifier stage eventually. And then, going from that and having pulse durations and the repetition rate, you can sort of help figure out the other stuff. So if you were to divide it by the repetition rate, which for us is about 10 megahertz, you'd get the pulse energy, and then you'd have to know the shape and sort of to figure out what the pulse duration and like peak power is within that pulse, and that's a little more complicated to do. But in terms of simulations for some of this 2-color stuff, I was approaching a peak power of what is almost the self-focusing limit, which you guys roughly touched on a few episodes ago, if I remember correctly.
Oh, and
In
lightning episode.
the lightning, yeah. So what actually happens there is that due to nonlinear effects, you have such a high intensity that you're varying the refractive index such that the beam then converges to a single point, and now it's just stuck at this one point, and it typically damages stuff. And for fibers, it's roughly the same for air. That's why a lot of high energy projects deal with photonic crystal fibers that have a big hole in the middle, hollow core, and they'll pump it full of some type of gas. And that way, they'll choose a gas such that your damage threshold now is a lot higher and you're not self-focusing.
So you said you could get somewhere around 10 watts, maybe. That's pretty good. I'm just thinking of like a red laser pointer. You'd point at your slides on the board. What was that like? What power does that have? Like milliwatts or?
If you're buying one that is off Amazon, they're really sketchy.
Oh, that's the one I have.
They actually a lot of the sketchy ones actually don't properly follow the safety guide. I've learned from a video. Somebody went and bought a bunch and tested them all out. They're supposed to be, I think, under 5 milliwatts legally. And a lot of them, I think some of them the guy had were like getting up to like 100 milliwatts plus, which is quite dangerous to your eye at that point.
Yeah, I think just like a regular laser pointer is pretty dangerous to your eye too, right? Like, I think we did a calculation at one point in a laser class we took where it was like pointing like a regular laser pointer in your eye. It was like 40 times more intense than staring at the sun or something like that. Or maybe it wasn't a laser
Yeah.
pointer, but maybe it was like
It
it was a laser
if I
pointer.
remember my
sorry.
safety right, it's something like if it's over like 1 or 5 milliwatts, you're supposed to have glasses on.
Hmm.
The more you work in laser labs, and not that we would ever do this, but you notice a lot of groups that are like, as long as the amplifier isn't on, the laser that's outputting 100 milliwatts is fine. And they kind of just shrug it off. It's like, as long as you're not bending down and like staring in the beam, you're fine. But you worry a lot about reflections off random things. So a lot of the times you're not supposed to have jewelry because, you know, if you're wearing a watch or a ring and you reach onto this table, you don't know where stray beams are, you could end up reflecting something anywhere.
Well, the other thing I think too is if you're working with ultraviolet light, you can't see it, so you got to be careful. There's like the ways you can.
we work in infrared, so
Oh yeah, infrared as
what
well.
we have is, yeah, so there's two ways of sort of viewing it. You can have these cards that have like this special material on it that light up so you can sort of track beams. And then you can have viewers so that way you can sort of see where it hits stuff or like how fibers glow.
I know in a lasers lab we were trying to repair a CO2 laser that was decently high intensity, but was a continuous laser. We didn't have any special cards, so we just used a piece of paper, and if it burned, that's where the laser was.
It's very dangerous, but yeah.
That's
Because these
sketchy.
cards, some of these cards are really expensive depending on the wavelength. Because I know like there's big cards that are maybe like 1.5 inches by like 1.5 inches square, and then there's some that are like 1 inch by 1/2 inch that are really small. And like some of those cards can get upwards of like $500-$600 US.
Expensive card. I have. This is my unrelated question. For the sake of time, I want to hear about your past research. So we're all friends. We all know each other. We went to the same undergraduate university. Similar theme for a lot of our guests. And you weren't actually an experimental. You didn't do experimental undergraduate research. You did more numerical simulation stuff. Actually, you worked for the same person Pheely did. So, what did you do during your undergraduate, and how did you end up? I guess why did you decide to study physics? What was your undergraduate research, and then how did you move on to do experimental physics?
So the undergrad research was two-step nucleation. And most of it was computational, so a lot of Monte Carlo, some random walks, and then a little bit of analytical work at the end that came out of that. So my first summer at our old university, I was working with the same prof that both you and Pheely were working for.
Oh,
Brandon.
right.
And that was me just sort of going, I know I want to be in physics. I know I want to do something research based. Let me find a prof that'll take a first year. And most of that was just learning how to type in LaTeX and not getting in the way of anything. He was kind of just, yeah, you're here. You can do whatever as long as you're doing something. And then the second year, it was sort of, I want to go with somebody who's actually doing something that seems cool. I found out after my first year I really like coding, so I switched to Peter Poole and doing a lot of the computational stuff. I really enjoyed all that, and I stayed with him for that summer and then my third summer as well. And I went to my third summer because I had already been with him for a summer. He said, you have some stuff, you have enough to sort of go and make presentations or posters or whatever, so I'm going to go and send you out this summer to go to a bunch of different conferences and just meet potential grad supervisors. And the big conference I went to was the CAP Congress. Happens in the summer, usually in June or July. It's about a week long. I did a poster presentation that year, and I mostly just sat around and listened to a ton of talks. And because I'm doing two-step nucleation, I was sort of in the condensed matter type of world. And so I went to a lot of the talks in condensed matter. And the way this conference sort of works is there might be 8 different sort of divisions going on. So there's the condensed matter, and then there's the photonics, and then there's the particle people. And you have to choose which one of like these sessions to go to because they're all happening at the same time. And I went to a bunch of these condensed matter talks, and I'm sitting there going, my research is really cool, but everyone else's research kind of sucks.
Don't tell
them. And I was like, I don't know if I want to keep doing this. And so looking for grad supervisors, I'm like, I want something interesting with somebody cool who's willing to take me, hopefully at like some type of reputable school would be nice. And I was planning for a conference of our own for that upcoming February for my last year where I was running it. And I had to get some guest speakers. And Donna had just won the Nobel Prize. And she was also giving a talk at CAP. And we had already emailed her asking her to come be a guest speaker. And after she gave her talk at this CAP Congress, there was a social. And so we went to the bar and I was just sitting there at a table all by myself because it just started. And she just walks in, sits right down next to me, and we just start talking. And so she had this former St. FX student come that had previously worked for her, and they were very close. Like I'm pretty sure if you asked her, that's probably her favorite student all time, Fraser. And he goes, "Look, I went to St. FX. He's going to St. FX. He needs a grad supervisor. Just take him." Because at the time she needed somebody who did computational work, and that's what I was doing. Even though I'm not doing optics, I'm doing two-step nucleation in sort of the condensed matter space, the chemical physics space. But it was sort of, I don't mind switching, and it's just like, as long as you don't mind also doing experiments, I'm like, that's great. That makes a well-rounded student. And then, so I take her as my grad supervisor. I get here, and I'm sort of like, hey, I'm doing computational. And it's like, well, the group got really small, and we have no one in labs, so congratulations, you get to go into lab instead of doing computational work. But it was also the start of COVID, and getting into lab was a huge pain, as you all know. There were a lot of times where it's like you might get in for a few hours once or twice, like once a week or once every other week type of deal, especially for the first about 9-10 months I was here. And then at that point, it's like nobody's been maintaining the laser's broken. Now I spend all my time fixing the laser, and we're finally at a point where I can split a lot of my time between simulating stuff, running computational data, and then actually going into lab and trying to do it for real. And that's sort of how I made the transition through all that. Yes.
Oh, I was just gonna say the power of networking. That seems to be a common theme. Like that's how I got my supervisors. That he had a student from X, and Pheely had a connection from Peter Poole for his supervisor. And I don't know about Patrick, but maybe there was networking involved there. Maybe, who knows? But yeah. So quickly. That's a really good story actually. That you kind of just got hired because you were sitting down, essentially.
I was just sitting at a bar, and then a former St. FX student came up, and bada bing, bada boom.
Quickly, what even is two-step nucleation? Very, very cool. Maybe not very quickly, but not a very long explanation.
So, starting with classical nucleation, which is sort of the one-step equivalent, is just how basically you go from one phase to being in a different phase. It's like the starting steps. And so a lot of that would be how quickly that phase grows, what shape it is, and sort of chemical potentials between these two different things. And all the two steps sort of is you can imagine the first step happening, it growing to be this big cluster, and then inside of that cluster you get a second step that transforms to a new thing. And typically in the classical sense, you'd be going from an unstable state to a stable state. But what happens in the two-step model is you go from a metastable state to something that's stable at the time, but isn't the most stable state. It transforms into an intermediate state, which is not stable. And then you flip to the final state. And it's the fact that the way these potentials work, that it's more energy favorable to get to the final state by going to this unstable state first, which sort of goes against what classical nucleation would say you should be able to do. And so we were doing a specific simulation on metamagnets, which Pheely mentioned. One of you mentioned the other day about metamagnets, and that's probably where you remember it. It's my talks about that. And so we started doing simulations of how these systems work, and what you sort of see is that the thermodynamic prediction of how the system should evolve doesn't match the classical. It also didn't quite match the two-step nucleation. It took them a really long time growing in this intermediate unstable phase to get to the final stage where it's stable, and you're kind of confused by that. And so then we went to go doing random walks instead of simulating this one specific dynamics by doing a random walk on a free energy surface, which is basically just, this is the free energy, put a particle here. If it's a drunk man walking around outside, which way does he go? Put him on a hill, he's more likely to go down the hill than up the hill. It's the same type of thing with the energy. And so we started doing that. But as we did that, we said, we're using simulated surfaces to do this simulated energy. Wouldn't it be nice if we had an analytical solution for this? And so that's where my one paper came out of, was we took somebody else's equation and we basically said this was his guess at it for what two-step nucleation free energy should look like. We took his equation, put it to our system, and said, hey, look, it matches, and let's fill in some of the theory holes for some of the parameters in this equation. And that's how we got our paper, which can then hopefully, and I'm still hopeful that I can do some of this research because it's kind of been stalled out for a few years now, is that now that we have this analytical free surface, we should be able to do the random walks, which should tell us why the system isn't moving the way we think it should, and then we can backtrack that back to the original dynamic system that I was working on when I first started.
I think so. Liam, you could just go read two-step nucleation, man.
We talked about
it's self-explanatory. Come
two-step,
on.
yeah, trivial.
You have one step, and now it's two steps, and
yeah, it's like doing it twice,
different.
buddy.
Well, it's doing it twice,
Yeah.
but the energy doesn't work, so you're confused.
Yeah, okay.
Yeah. Anyways, before we wrapped up to the story, Dean, what are your hopes and dreams? What would you like to be? Who would you like to be? Or like, what do you gain from this? Are you trying to go in industry, or do you try to gain some skills to be a prof? Like, what do you like to do?
Who knows? You know, I've been through so many different phases of, oh, I'll finish undergrad and then I'll apply to med school. Now I'll do grad school and become a prof. No, I want to go into industry. You know, finance would be cool, make a lot of money. Right now, I think I'm leaning towards becoming a prof. I don't always like teaching, but I've been told I'm really good at it. And it's not the worst. And I feel like it would be better once you're in control, like in more control of the class rather than being a TA. I don't know if you guys feel the same, but a lot of times I'm being a TA and it's like you're stuck in whatever somebody else wants you to do rather than, you know, this is a better way of doing it and I'd prefer doing it this way on my own. Liam,
That's
you look
how
like you
I
agree.
feel. Yes, 100%. I love teaching and TAing, but sometimes I'm like, oh, I don't like this I don't like this prof's marking scheme. I would do it completely differently, or it's like I would use very different teaching styles. So I'm also, yeah, I agree with that.
It's because, like, I think the problem with a lot of profs is that, especially at large universities, is you got to come with research if you're a prof, but a lot of the profs come just for the research and are stuck with teaching, rather than somebody who actually wants to be there and teach, which is sort of where I'm leaning to. Even though I have research and I'm capable of doing research, and I'm sure I'll do research if I go down this avenue, but I'd like teaching, I think, a bit more.
Yeah, you didn't strike me as a teaching type, so I was a little surprised to hear that.
I don't like it in some sense because I'm the guy sitting there going, God, the students are stupid sometimes. God, why are they so stupid? And that's kind of why I want to be a teacher. And like, I think I know better ways to help with this, but it's hard to do it sometimes with the way stuff is structured. I've been told I'm good at it, which is weird being told because I feel like I'm bad at it. And then people are like, no, you're really good at it. I'm like, what?
It's the imposter syndrome kicking in.
A little bit.
All right. I think that's a good answer. That's a pretty decent answer. I think we're gonna move on. Thank you, Dean. And I think Liam has a story for today about, I don't know, star or something.
What are you talking about?
I'll let Liam take over.
What are you talking about? We have to.
Oh, and before that, get Patrick to talk about how to reach us.
Yeah, so before we get to whatever Liam's story is, there seems to be some confusion, even though we have it right in front of us. There are many ways in which you can contact us. Our primary method is through either our Instagram or Gmail. If you want to send us an email with questions about an episode, suggestions for episode ideas, or if you want to get in contact with any of us, you can send us an email. We're hyperthesispodcast@gmail.com. So you can find us there. You can find us on our Instagram. We're found at the Hyperthesis. So there we post updates. We post whenever we post an episode, so you can always get updates. We also post some behind the scenes photos and some memes. I keep pressuring Liam to post some memes, and he is doing well with that. There's some good ones on there. We also have a YouTube channel. We have not updated it in a while. There's just some processing pipeline issues and delays that we've been dealing with, but we will eventually get more videos uploaded on our YouTube, and they have been masterfully created and programmed by Pheely. And other than that, you can find us pretty much wherever you find podcasts, whether it's Spotify, Google Podcast, Apple Podcast, Amazon Music. We're pretty much on every podcasting service. And Dean, if people would like to contact you in any way, how would you prefer to be contacted?
You can just
if at all.
you can just contact me through my school email. I'm sure you guys can probably put it in the description of the video or something.
Sure, we can do that. So if you have questions for Dean about his research or want some way to get access to Donna Strickland, feel free to send Dean an email.
She needs more.
Got an eyebrow.
She needs more
raise at that.
students, like you were saying, right? There you go.
She does, but shh.
Okay. You didn't.
That means more funding for me.
All right. Fair enough.
There.
All right.
So yeah, so feel free to like, rate, subscribe, do whatever you want to do, and get in contact with us if you want to.
She also does need more students, but I will say one more thing that she's very interested in is she is looking for postdocs who have good experience in nonlinear optics and high intense laser stuff.
There you go, postdoc. Get on it. All right. So Pheely was actually confused because I last second changed what my story was going to be about and didn't tell him. So today's story is going to be topical, and it's going to be about Donna Strickland because, Dean's supervisor, Nobel Prize winner. Usually in the past when we tell stories about people, they're usually dead. But this Nobel Prize winner is very much alive, as we've heard. So if I say anything wrong, Dean, correct me, and I might ask you for some clarifications, but we'll see. So Donna Strickland is a Canadian physicist, and she changed the field of these high-intensity pulse lasers with her creation of chirped pulse amplification with her supervisor, Gerard Moreau. I might have pronounced that wrong, but Dean shook his head yes, so I'm happy now. So she's currently a professor at the University of Waterloo, which we know now, and she was born on May 27th, 1959 in Guelph, Ontario, which is very close to Waterloo. Her mother was an English teacher and her father was an electrical engineer. After she graduated from high school, she decided to attend McMaster University. Yeehaw. The greatest. No, kidding. She attended McMaster University, so Guelph is actually pretty close to McMaster. It's about like a 45, 60-minute drive away. And I know this because I go to Guelph for band once or twice a week. So I'm up Dean's way pretty often. So when she decided to go to McMaster, it was because she decided ultimately to go there because their engineering physics program actually included lasers and electro-optics, which was areas of science she was really interested in. And it turns out that she was actually one of only 3 women in her graduating class of 25. So she graduated in 1981 with her engineering degree, or her bachelor in engineering. And just a side note I've noticed is that when people win Nobel Prizes, the universities really jump on that. So there's all these photos of Donna Strickland everywhere, even though she only won her she went to McMaster for her bachelor, but she got her Nobel Prize at a different university for work there.
I think one of the important things for her also is that when you win the award, lots of people want you to come work for them. And lucky for her, I think she was due for a contract like a year or two right after she won the award. So it was very good bargaining power on her behalf.
Yeah.
In order to sort of determine to stay or go.
Yes.
Because a lot of these profs, they get tenure and then they're basically stuck at that university forever. But she was lucky in the fact that right after she won the award, it's like, okay, I can put in a lot of negotiating power right now to get a lot of stuff.
Yes, the Nobel Prize winners can kind of do whatever they want, I think. Yeah, so she wasn't actually, I read this on Wiki, she wasn't actually tenured when she won the Nobel Prize, and it was by choice. She just kind of didn't want to be. She's tenured now, I believe, once she won the Nobel Prize.
Yeah, if I remember correctly, it came down to the fact that she just never bothered applying. People were like, "You're a woman, and it's unfair they're giving it to you," and it was just, I never applied. I was fine with where I was.
Yes, so there's benefits to being tenured, but also if you get tenured, you're kind of stuck at that university now. So I think, yeah. And anyway, she wasn't tenured, but she is now. upon her own choice. And that's kind of an interesting way to look at it, because most people will just jump. They want tenure more than anything. So that's kind of interesting. But I always wondered, when they put up these photos of the Nobel Prize winner everywhere, like, do they have to get permission for that, or because she went there, can they just do that? I don't know. But anyway, I'll leave that point there, and you can think about it. So, um, Strickland went on to study in 1989 at the University of Rochester, located in the state of New York. So New York is also close to McMaster. McMaster is about a 40-50 minute drive from Niagara Falls, which is the border between New York and Ontario, and then Rochester's close to Niagara. And she did her PhD at the Associated Laboratory for Laser Energetics, supervised by Gerard Moreau, which is actually one of the 3 people that she shared the Nobel Prize with for chirped pulse amplification. So a very heartwarming Nobel Prize. And they developed this chirped pulse amplification, which was this experimental setup that could raise the peak power of laser pulses. Because at the time, there was this limitation that the maximum intensity of laser pulses would reach the gigawatt range. But this self-focusing would actually kind of melt the components or damage components that create the lasers themselves. So you couldn't create high enough lasers without destroying your laser producing device. So they developed this famous technique, which we've said many, many times, chirped pulse amplification, and that overcame the limit. And we talked a little bit about it, so I won't describe what it was. But it was able to actually generate these ultra short optical pulses in the terawatt to petawatt range. And chirped pulse amplification has allowed for many kind of tabletop terawatt lasers in physics and also in the real world, which is why she got the Nobel Prize for it. Because it's changed the field of lasers. So I'm going to talk about 4 or 5, I forget how many, kind of applications of chirped pulse amplification in the real world. So one of them is it's been used for cancer treatment in the brain. It can accelerate protons for proton therapies that are used to treat deep tissue tumors which develop in the brain. And it's the only practical way we have currently of getting rid of these tumors, because it can very precisely deposit energy to where the cancer cells are, but without destroying any other part of the brain. So that's already one extremely useful application. It's used in laser eye surgery, so that's kind of like the common one you hear people talk about when they talk about chirped pulse amplification. It gets used to quickly slice open the lens of the eye without actually damaging the surrounding tissue. And in the US alone, nearly 10 million patients have had their vision corrected with this procedure. That's also very widely reaching. Third application is used for kind of the creation and cleaning of materials. So using thermal energy to remove material from metallic or non-metallic surfaces is kind of like laser cleaning. You can kind of abeliate, that's the word I think, dirt and grime and stuff off of surfaces, or you can use it to kind of very precisely shape very tiny devices you can use in electronics and things like that. So an example is you can the material used for smartphone touch screens use certain ones use chirped pulse amplification to create them. And then in kind of more fundamental physics and science research, it's used all the time. Can generate these huge quantities of charged particles in light for heating matter. So you can actually stimulate stellar conditions on the insides of suns. So we can I study analog gravity. I study things that look like black holes. You can create things that look like stars in the lab and study them, which is kind of cool. And there's all kinds of other experiments and applications in physics alone where you can use this chirped pulse amplification. You get these ultra high laser pulses to kind of probe things or all kinds of stuff. Oh, there it is. Sorry, in my notes I couldn't find what I was looking for. One example is you can use it to probe dense matter and even nuclear structures, so you can actually lead to visualization and better understanding of the fundamental nature of atoms, which actually has applications in nuclear fusion research, which is a very important thing for powering the Earth. So yeah, that's kind of the story of Donna Strickland and how her Nobel Prize research actually has really changed the world, because I know a lot of these other Nobel Prizes, it's changed the world a lot, but the chirp pulse amplification actually is really seemed to change a lot about like mainstream world. I guess like Bose-Einstein condensation is this thing I study, and it's changed the world, but it's kind of changed the world of physics more so than it's changed anything. Whereas chirp pulse amplification has had a lot of direct consequences for the average human.
All right. Thank you, Liam, for the story. And this is going to be the end of this episode. Thank you, Dean, for coming and share your story with us. And I will talk to you guys next week. Take care.
Bye, everyone.
See ya.
Bye.